Welcome to the afternoon session. We will now hear from Professor Feng from Linsa, who will talk about the finitary form of meta theory of mathematics. Welcome.
Thank you. Thank you. First of all, thanks to the organizer of the conference to give me an opportunity to explain to you what I've been working in the past 2 years. It has been very, very lengthy, hard working for 2 years. The whole manuscript of this project currently is about 1,700 pages. So I cannot tell you the details, but I'll give you the outlines and some byproducts. As time goes on, I realize what I'm working on is actually try or attempt to provide a formalization of metaphysics in a narrow sense. So narrow that I gave a name called a meta theory of mathematics. And this is not something the project I intended to have at the beginning, but it was because I was asked to teach the Tsinghua University philosophy department to give a course called Philosophy of Logic. It's a subject completely new to me. So going on to the field, I realized there's something I should work on. Many years back, or more than 2,000 years, Aristotle was trying to find his first principles. After he finished his physics, he was working on the metaphysics. And that's the place he wanted to know which are the first principles that we must assume before you go on in thinking. And this is trying to merge something has been done almost like 150 years ago by Frege and Cantor, and almost like 120 years ago by Zermelo, and then 114 years ago by what Russell and Whitehead had been done. So I will tell you what exactly it was. First of all, I will tell you what I've been working on. I call a specifically finite meta theory, in short, CFGFC. C stands for Cantor, F stands for Frege, Z stands for Zermelo, F stands for Feng. The C stands for axiom of choice. The last three called the GFC in set theory, or formal theory. However, working in set theory, I realized I myself completely take Frege as granted. When I tried to do the calculation, I realized without Frege's first order logical rule, we don't do anything. We cannot really claim that we have some proofs. You can't really do it. So that's why I need a Frege in front of Z. So that's the CFGFC. I will tell you what the theory really is. And then, as a byproduct, I will explain to you, when you do the calculation, you find out many as people trying to define finiteness. Of course, as working in set theory, we have a very good way to define what something is called a finite. Like Professor Chong talked about this morning, the finite natural numbers were standard ones. That's where we have the axiom of infinity. Everything very smoothly interpreted. But without axiom of choice, axiom of infinity, what can you see about finiteness? Dedekind was the one trying to define it. Frege was the one trying to define it. Frege was using purely logical rules, but it's very complicated, using so-called one-to-one correspondence. And Dedekind doing the same thing, but he was using more or less a set theory language. Of course, we know Dedekind's definition of finiteness is only, we will say, it's only a sufficient condition. Without axiom of choice, his definition is not really catching the essence of finiteness. Then I will try to give you one very interesting application to philosophy. on Quine's theory of logical truth. This is really philosophy. That's why I say we are formalizing in some sense metaphysics. When you have that, you can answer many questions in philosophy just like we do mathematics. That's why the formalization is important, has been proved. All right, let me explain to you what the finite matter theory really is. I must tell you, it's very lengthy work. I will give you the key ideas, but not the details. First of all, what is the motivation questions? Well, the real question is it possible to develop a formal finitary matter theory as foundation of mathematics in such a way that all deductions within the matter theory must proceed by applications of explicitly stated rules to avoid entirely any usage of informal intuitive inferences? If you open the mathematics by Kleene, in the introduction, he says very clearly, working in mathematics, we must work in informal, intuitive deduction theory because we don't want to get into matter of. So here I say, there is a way we can offer or turn around. Mathematics can be set down in a formal, deductive, without intuitive inferences. Everything is formal. The only exception where the intuition stands, the intuitive part is the semantics. In this formal theory, there will be no formal semantics at all until we develop sufficient material where set theory is really in full power. Then we can have a formal semantics to be defined. So the first part, no semantics. However, you do keep in mind intuitively what you're trying to do. Just like we have natural numbers in the concept, or before we have rigorous definition. Okay, it's whatever you think intuitively it is, but we're not going to use that. This is always a stimulating question to ask. When I teach set theory at the Tsinghua University, a student asked me, well, working axiomatic set theory, do you need logic? Sure. Without logic, we can't do anything. I think I explicitly mentioned in my set theory introduction, second volume, how we're going to apply logical rules. And then I teach mathematical logic. Students ask, do you need a set theory? Sure. Without set theory, mathematical logic cannot really do anything. Okay? They said, okay, which one goes first? It's simple, obvious, everyone must ask the question. Of course, working set theory, we have a very good way to answer. With a hand, well, don't worry about it. Every theorem proof is finite. We can do it. But how? All right, so the central idea of a possible answer is to critically merge Frege's logical scheme with the Zermelo's formalization of Cantor's set theory. That's where CFGFC come about. So how? So the symbols of the simplest formal language are the following. These are standard logical constants. Everybody say it, you use it. However, there's a long logical symbol called absolute relation. This is meta non-logical binary relation symbol. Some philosophy like Quine actually argued this symbol is not a logical symbol. If it's not logically, what it is? Well, if you go back and look at what Aristotle wrote, Plato wrote, Frege wrote, there's always an intuitive concept called belongs to. Cantor used this one to formalize or formally express what do you mean by belongs to. It belongs to relation, and that's metaphysics. So this is the one you can use. You want to develop concepts, and that's the one. So using the very simple symbols, you can develop language. Again, we have a very limited hands, resources. I give you overkill. You are only allowed to use 100 variable symbols, 30 to 399. It's overkill because so far I don't even need the 50. But I do need many tools so that I can manipulate. I can change variables. Every mathematician knows how to freely change variables. But why you can do that? You need a reason. That's why your Frege's rule will help us. So what do we do? In the simple language, we try to build up a very simple language by formalizing what a Frege's logical scheme. Again, you have to eliminate because we try to be finitary. Because you don't get a long list or infinite list, okay? All right, so now we can build up the needed specific set of formulas by leveled construction, level by level. And this big number is again overkill. But right down here is to convince you there's a huge table. You just work every specific concrete formulas and list on the table. Okay? And then you can build out these primary formulas, level 0, use epsilon relation, use equality, okay? Variables. So these are the very simple formulas. This is set theory, everybody does. But here we only required, you're not good at that many, I just need this many samples. This many formulas is a big matrix, okay? And that's it. Start from here, you build up the next level by taking the negation, and you take the implication, and you take this universal quantification. The level limitation is always been kept in mind. Why? Because later on, you develop a certain theory, you just need that many specific formulas. I will tell you where I'm going to stop this limitation to free my hands. As everybody uses, we have infinite many variables. Where do they come from? We have to produce them. Okay, it's not given by somebody else. We produce them. By this theory you develop in, you have enough resources. Yeah? Yes, variables are only limited by that. I just allow you to use that many variables, nothing more. You'll find out because the formulas we are to develop, the basic theory, you do not need that many variables. Okay? Because the formulas we're using are really simple. They are really not that complicated. More than enough. I tell you so far, over 1,700 pages have been written off. More than 10,000 formulas have been formulated. I do not need a number of variables more than 50. You just keep changing, okay? You can do it. All right. So by this way, I mean, this looks like you would ask, you are doing recursion, right? It's recursion, but you up to a limited level. It's very specific. You do them up step by step. We don't have a general recursion theorem here. We do not use it. All right. So the CFZFC consists of a specific list of fundamental Frege rules in the simplest language of set theory, which we call the applicable Frege rules. Okay? And then a specific list of fundamentally similar axioms of set theory, we call the applicable Zermelo axioms. By the way, when you do the calculation, you find out that times you apply Frege's rules is almost like 10 times of Zermelo's rules. If you apply 1 time Zermelo's rule to get something new, you actually need many Frege's rules to support why you can do that. You want to prove something, you need similar Frege's rules. So that's very important. I just realized as working in CFA for so many years, I myself did not realize we are actually with the big help of Frege until I've been doing this in the past 12 years. I mean, like for example, Professor was talking about the probability in the morning. He has all the non-logical axioms, first order, inductive scheme, etc. There's no Frege's rule there. But if you really write it down a formal proof, without a Frege's rule in logic, you're not really getting anywhere. That's the truth. But we take them for granted. Every mathematician takes it for granted without even realize you need that. Many things we do, practically we thought was correct. But why is correct? Frege said you can do this because of that. That's the first principles of Aristotle was searching for. All right. So now we have the built-up standard deduction rule, this modus ponens. So we have a formula of implication of this type, and you have this, you can conclude that. That's standard, what we call deduction rule. Okay? Every mathematical logic course teaches us that. Standard. And then you look at a proof. Again, that's a standard definition of proof. You give a specific proof, a sequence of formulas which are within the domain of the formulas you are using, but sequence has a limit. As long as you can write it down, it's very concrete. I don't worry about the length. Okay, as long as you write it down, as a satisfy the property, that's a proof. Okay. So basically, the first three are either from the gamma, the specific set, or is applicable Frege's rule, or you get the formula by the modus ponens. So there's a standard way of defining what a proof is. There's nothing new here. Okay, then what we need is those Frege's rules, Zermelo's axioms, we are going to sufficiently build up V omega plus 6. You'll find it quite interesting. Why V omega plus 6? Everything to code a logical samples or private languages, V omega is good enough. Everything is there. Hereditary defined objects. But we do need a V omega plus 6. Why? Because we need a very standard recursive definition theorem. What I need, for example, everybody knows we can do this summation of numbers, any finite many of them, called the big sigma. If you want to show this function exists, you need something that living in V omega plus 5. Then you can define recursively the sigma operation. But of course, sigma operation is what number theorists are interested in. We are interested in too. But we're really interested in how you merge finite many sequence of sequence. Again, I can do the summation, where we call the star operation. That's again, you need something in V omega plus 5 to certify your recursive definition is valid. So that's why the complexity comes into. Okay. Then we can sufficiently code the material, either for general first order language and the meta-logical concepts. As long as you have that, anything in your mathematical logic, you define, they are coded material there. They are as sets, just as natural numbers are sets in set theory. So every logical concept becomes a set. It's there. So that's the reason we have this formal definition. And now, of course, logical samples, variables, constants, function samples, predicate samples, and terms, formula, and substitutability. And this is a very complicated definition, but you can do. It's better, simpler than what good coding in natural numbers, for sure. Okay, set theory has an advantage. You can code the objects as a set, hereditary objects, finite. But the whole coding system is simpler because good as coding using our Charles remainder theorem. And the whole coding system is rather complicated. Here it's simpler. And then we have the frequency rules, and then we have the proofs, and the satisfaction relation. So the semantics come into, you can define. And you can define validity, and you can define what I mean by logical truth. They are all definable level by level in the synthetic part. And then, of course, logical consequences. So these are the standard first order logical material. But we do use this formalization to code them in a formal system. Again, we do this, it's really formal calculation. But do that, you really know what they call a predicative calculus. It is a calculus. There's no semantics. But you do remind yourself what I'm doing means what to me. And that's intuitive semantics. Okay, so there's some case. People 70 years ago treated mathematics as working in the intuitive, informal inferences background, okay? I mean, when I was studying mathematical logic, my teacher would come in, give us what the mathematical induction is, what the recursive definition is, but it's all working on intuitively. So we have intuitive natural numbers, we have intuitive mathematical induction, we have intuitive recursive definition. That is intuitive. However, the real important thing in logic is what they call deduction theorem and universality theorem. These two theorems are proved by induction. That's why you do need the informal induction if you want to carry that proof that way. But we can avoid this because what? Because you don't need a deduction theorem. You need its algorithm. An algorithm that translates one proof effectively into another proof. That's why you don't need the induction. So what is the algorithm? The input is what they call a gamma union another non-logical axiom theta. You have a proof theta 1 through theta, and this sequence is a proof in different theory. Here is another proof. It's much longer. How long? It's almost like 4 times longer. But this by translated by an algorithm. What is algorithm? Here it is. You have the input, and you work out step by step. If that happens, do this. If that happens, do that. After it's done, you have successfully produced another proof. And that's the proof you are looking for. That's why the theorem still holds, but you don't prove that by induction. You just carry out this algorithm. And the algorithm is a finite object. We have to agree on that. You write it down. The instructions are finite. They're actually there. It's a finite objects. No mathematical induction is needed. Similarly, for the universal quantification, it's the same as a method. You translate one proof into another. That's the reason you don't need a mathematical induction. Again, the length of the produced products is almost like 4 times. So what we need is 2 algorithms. Whenever you try, and these are very important methods when you simplify your formal arguments. It's very important. We use almost every page because that definitely reduce the length of the whole formal proof. They're very useful, very powerful. But you don't need an induction. You just write down the instructions in this algorithm. Okay? So don't worry about the details of the algorithm, but it works for sure. Okay, so we have these 2 algorithms, we have these 2 methods, we can carry out the formal proofs. Then we can have the whole system set to work. So as a byproduct, I explained to you how we should understand the finiteness and the basic arithmetic. And this is just a byproduct. In a formal computation, You can do this. So here's the definition, the very fundamental one. Let's call it ordered pair. Now we are in the formal set theory part. Okay, this has really definition what it means by the ordered pair. This is a set. So an ordered pair is a natural discrete linear order if it has the following property. First of all, either the domain is empty or the following is true. They are linearly ordered by this binary relation. And if A is not empty, it has a minimum. If A is not empty, it has a maximum. It's a very simple structure, but very fundamental. Everywhere you see in the life, daily life, you see objects of this type. Everywhere, okay? If you really want to think about this, it's like a symmetrical way of ordering. Find objects. Okay, so based on this, now we can define the standard operations. Okay, you can add them together. You can take the product. You can take the exponentiation. Okay, so this type of objects can be manipulated in set theory by defining the standard combination. The reason we're interested is we want to use this structure to define what is something called finite. So an object is finite if and only if there exists a binary relation on this object, which is a natural discrete linear order. This object we call a finite objects. Okay, now you can compute because of the previous operations available to us. You can prove. You can add two finite sets to get a finite. The power set of it is still finite because you have the exponentiation. Okay, and etc. So basic property of finiteness can be calculated. However, there are some difficulties in the arithmetic part, I'll tell you. All right, so basically, given two similar structures, you can prove that either they are isomorphic or one is isomorphic to proper initial segment of the other. So that's a standard thing, nothing really striking. All right, so of course you need a basic theory to work on, which we have developed long enough. How long? Take about 500 pages before we reach this part. Everything is formal. Remember that. You have to do the calculation to guarantee that it works. So now we have this the sums, products, exponents. They are invariant and isomorphism. So that will give us a possibility. We can use them to represent our understanding of natural numbers or finite objects. All right. So arithmetic question arises. Here's the question. Is the sum operation commutative? Is it associative? Okay, you can define it. You can add them together. Can you prove this commutative? We know that they are commutative. But your system must convince me you can prove it's commutative. Is the product commutative, associative? Similarly, exponential operation commutative, associative, etc. Basic arithmetic. Okay. Now we need something from Dedekind. I call the Dedekind principle. It's the following. If there's a binary relation such that, in other words, if there's a finite, then every injective function from x to x is surjective. The conclusion is what Dedekind used to define his finiteness. Okay? That's what the history is. What we are saying is, if x is finite, then every injective function from x to x is surjective. That's what they call the Dedekind principle. Dedekind used the conclusion to define his finiteness, which we know it doesn't really catch the essence of the finiteness, because without axiom choice, a Dedekind finite set can be infinite. Okay, that's the problem. But this Dedekind principle, you put it this way, in other words, you limit your applicability of this injective implies surjectivity You don't want to get everything like this, but you only allow look at those carry this particular linear order, that structure, and that works. Okay, the theorem says if you have this, then the standard Cantor-Bernstein theorem can be proved. And also, you have this categoricity theorem. If they are having the same cardinality, then they're actually order isomorphism. And this categoricity theorem is so important that you can prove all the associativity and commutativity becomes an easy matter. So that's why I take this Dedekind principle in addition to what we have had before. So based on this, we can show that the sum is commutative, is associative, products is commutative, associative, products are distributive to sums, and the exponential laws are true for the natural ordered sets. So basically, arithmetic can be proved. However, the equivalence classes of this order is a huge thing. It's a class. Every equivalence class really is a class in the universe of sets. Huge. Question is, what are the canonical representation things? Okay? That's where a usage of axiom of infinity. If you assume the axiom of infinity is added, then you can prove that Dedekind principle is true. You can prove that it's a theorem. And you have a very natural way the elements of omega can be used to represent the equivalence class. Of course, you can define something called a transitive sets and the transitive order, the absolute relation. Okay, that's what the omega is defined. This is rather standard. You can do this. All right. So that basically explains the axiom of infinity does not really apply any rule for the basic arithmetic. However, it solves the standard representation problem. You have very nice objects to represent the equivalence classes so that they have very beautiful natural numbers. That's why when I started set theory, I thought this is really a great thing. Okay, von Neumann's idea to define the natural numbers in this way, it's the triplet of products. So nice. But if you go back to the history, people define natural numbers in a very different way, intuitively. That's the actual axiom of infinity, because only potential infinity are allowed. But we still have arithmetic. Why? That's because there's something behind it. You don't need the actual axiom of infinity until you have to find a canonical representation for each equivalence class. Of course, for some, you do have, but not every. If you want to have every equivalence class of such an order, you do need an axiom of infinity. That's the key. Because in some classes, it's quite natural. You can have a very looks like a natural number in the class, but not every class has that. So that's why you need axiom of infinity to cover the whole thing. That involves. Okay, so now let's look at the second byproduct, the Quine's theory of logical truth. This is philosophy now. Okay, mathematics basically can be carried out without any difficulty, but philosophy, if you apply set theory or this formalized theory to do it, it's an entirely different thing. And it's quite interesting and challenging. That's why I say, I convince myself it's possible in a narrow sense, this formalization can serve as foundation of metaphysics, because so many basic concepts, whatever you talk about science, are representable in this framework. So Cantor this because Cantor's epsilon in the formalization, the symbolization, solve the problem something belongs to something else. And then you plus the logical operations, it works. So let's look at what Quine's theory of logical truths. Here are the questions. Philosophers ask, what is logic? Or what are logics? And what are truths? What are logical truths? What is the ground of logical truths? How do we know a sentence is logical truth? These are the standard, the basic questions of philosophy was asking. If you look at the so-called philosophy of logic, you open the book, very few pages going on, you look at all the questions at least there. Okay, so let's look at how should we answer the Quine in 1986. He defined in a very general way what a logical truth should be. According to his writing, a logical truth is a sentence that cannot be turned false by substituting for lexicon, even under supplementation of lexical resources. This is a purely philosopher statement, okay? And you turn a little bit further on page 95, he restated his definition. He says that a sentence is logically true if all sentences with that grammatical structure are true. And I was told Quine's definition of logical truths is basically like something being determined in the philosophy community, and that's the definition. People take this as the definition. All right, you can find out that's a philosophy of logic published in 1986. By the way, that's in this book. Quine did his analysis where the epsilon relation cannot be a logical constant. But he did not say if it's not a logical constant, what's the usage of that symbol? We're trying to give an answer. Okay, so we shall make a clear distinction between logical truths and laws of logic. Okay, so how are we going to do it? We will see that a sentence is logically true if it is an instance of the values of a law of logic. So I will tell you what a law of logic is. It's a mapping. It's a set. It's a function that has certain properties. So in set theory, for us, just like an addition of numbers, it's a function. It's there. It's an object. It's an existence. So a law of logic, again, it's a function. It's a set. It's existence. The values, on the other hand, is again a set. Those values of such a laws of function, logic, are logically true. So we get very, very rigorous, clear definition what the philosophers were searching for answer. By specifying what the laws of logic are, we try to remove possible ambiguity of course, the grammatical structure. Okay, so philosophers statement of grammatical structure. Of course, if you have linguistics, we know what the grammatical structures are. Language tells you. So here are the questions. How do we know a sentence of an objective language is an instance of the values of a law of logic? How do we know it's logical truth of a potentially logically true sentence? Okay, it's possible there might be a candidate. How do we know it's actually logically true? Our position is that no one can declare a sentence to be logically true before it's verified. That's very important position, because in philosophy's argument, they don't really care how you can verify it, since logical truths are granted, given by somebody else. How do we verify that a sentence is logically true? So these are the things we can answer in this formal theory. First, Any verification is models of objects of certain specified type abstracted from reality. That's what we do. We try to find the object, try to understand it, and we try to give a representation in a suitable language. That's what a human really, if been working for so many years, the civilization. Of course, it's not as some philosophy claims this is just like a game. No, it's not. We are very clearly standing by. We are trying to understand reality, try to find a representation by abstraction, this type of stuff. That's the first position. Secondly, validity of atomic propositions are completely decided without any syntactical involvement of logical constants. And these truths serve as the basics of the verification of logical truths. This also, I make it clear, these atomic facts or basic facts has nothing to do with logic. It's from science. It's not by logicians or mathematicians. It's from the science part. People working in science will decide which atomic facts are true, which atomic statements are false. Logical constants has no impact on them. That's why sometimes people overstate their logical functions. Since truth is the main object of logic is care of. But actually, I don't think so. Those are the basic things, true or false, is decided by scientific activities, not by logical practice. We cannot do anything. Everybody would agree. We studied the Boolean logic or Aristotle logic. This truth function of the atomic things, the variables, were given. We consider all possibilities. They are given to us. A logic only based on that. Similarly, if you look at how tasks is defined, the validity in the structure is in set theory. It's a particular structure there. You have particular relations. True or false is decided within set theory. It's not logic. And then you build up recursively for the composited formulas which are true or false. That's why logic plays. It's not the atomic part. So understanding this, then we can see that the satisfiability of statement within a particular model depends on its logical form. That's one thing. Philosophers emphasize the logical form. And the syntactical type definition. And this part, philosophers mostly ignored. But they said were grammatical structures. Of those atomic propositions occurred within the statement, the two things are important. What is the logical form and what is syntactical type definition? I will use set theory to explain to you exactly what are logical forms, what are what we call the syntactical type definition. Okay? These are heavily influence what are composited statement is true or false based on the given atomics. So let's consider first of all the logic. In this logic, the logical constants are standard ones: negation, implication, or, and, if and only if. For every xi, there is xi. And then some of them are definable, we know this. So excluding equality sign, and for each individual variables, we consider for all xi, the xi as one logical constant respectively. Okay, so these are the things we are considering. And then a logical n-form, or simply n-form, of logical constants is a uniquely readable, logical, meaningful sequence of logical constants and n gaps, in which the n gaps are to be filled by n formula of first order language, and each gap can be and need to be filled by exactly one first order formula as a subformula in order to form a single formula. Well, this is tell you intuitively what it should be, well, it looks like a definition, but it's not really a theoretical definition. Here we go. If you use this tool as a gap is a positive logical one form. You put a negation sign in front of this gap, you get a negative logical one form. Okay, that's one form. If sigma is n form, then not sigma is an n form. If sigma is n form, tau is another m form, then sigma implies tau is n plus n form. If sigma is n form, then for all xi, sigma is n form. So number of forms in such an expression, you count how many gaps inside. And the gaps are the spaces where you can put something in. That's it. You can do this recursive definition in set theory. We have developed long enough, powerful enough to define this. Okay, so similarly, you can define if sigma is an n form, then xi sigma is another n form. And if you got two n form or m form, you take the disjunction, and you have n plus m form. Again, you can take the conjunction, you get n plus m form. You have if and only if, it's another n plus m form. So you can see the logical constants does not contribute the number increment of the forms. It is the number of the gaps. How many things you need to fill in? Like I have 4 pockets, you have 8 pockets. The number of pockets is the form. Of course, they are organized in terms of the logical constants. That's why you call it logical form. It's not an arbitrary form. All the composited rules are standard by logic. Okay, we follow the same way to build up the forms. All right, so given an n form, a syntactic way to fill in the gaps of n form is to specify a syntactical type definition of a sequence of n formula out of all sequences of n formula. Suppose you have n forms, the n gaps you want to fill in. So therefore, you are considering a sequence of n formulas. Okay? So which sequence of n formulas are supposed to fill in these n forms? Then you have to make an effective distinction. And that's what definition is. Okay? All right. Suppose I have a sequence, psi 0 to psi n, I have n plus 1 many of them. So a syntactic definition is an effective specification of syntactical sequence relation among the formula in the sequence, such as the ith psi is the same as the jth psi. The ith psi is a result of logically replacing free variables x1, xt1 to xm of psi j by terms tau1 to tau m respectively. So every such criteria is effectively checkable given a sequence. All right, so you can define whether the sequence satisfies this type of definition or not in a very effective way. That's what they call the syntactical type definition. So here's the definition. A law of logic is a fixed syntactical way to fill in the gaps of some n form with a specified syntactical type definition of sequences of formulae of length n, so that the results of replacing the sequence of n gaps by any sequence of formula of length n of that particular specific type sequential respectively are all true when properly interpreted in all possible first-order structures known in the metaphysical world. That's how we define it. Okay? That's what actually we do in first-order logic courses, except we don't say this particularly explicitly in the set theoretical terminology. Give you an example. Here I have a two form. Okay? Connect these two forms by a very simple implications. And the type definition is being equal. the first one, the second one, the same. Okay, that's why standard. You can see there's an excluded middle or self-implication. We know this is a standard logical truth, right? It's always true. The psi can be any formula. So that defines one thing. You can figure out the forms of this way. So you write it down. Here BTS stands for, basically that's the formula. Okay, that's a set of all the formulas, first order. So this gives you a mapping from the BDS to what I call the BRZ. BRZ means always true. It's provably true. Okay, you can define it in terms of Tao-Shi truth definition. It's definable. Of course, by the way, they are all subsets of V omega. Okay? So this is our V omega, the subset of omega here. So therefore, you have a mapping. So logically true, the value of this law of logic, that's why this psi here, you write it down, the value is logically true. We all know, we proved this, right, in the mathematical logical course, where everybody knows. But it's a value of this law of logic. It's a mapping. The domain of this mapping is the entire set of formulas. Okay? So that gave you a first example. A second example I give you is this. And this actually, if you look at the first order logic course, this probably is the number 7 formula. Composition. This is that how you calculate the conjunction. The law of conjunction there. Okay? So that what you need is the following. You look at here. First 3 formulas are the same, except this one. You look at this one. So therefore, the formula really is this type. Okay? That's how you go. This is logical true because you can show this is a binary function. Okay, in the Cartesian space of the formulas mapped into BRZ. The logical true because you can verify this. First order logic course did verify it. So you can tell this particular value of these 2 formulas under this law of logic mapping is valid in every first order structure. It's logical true. Okay, so here's the Frege's first rule. If you look at the first order logic, the first rule, longest one, or sometimes put the 7, depending on how you prefer it. This is a Frege's rule. You look at the Frege's book. Frege's book, this is the first one he stated very clearly. That's the law, the first rule. So therefore, you look at the definition that the first 3 and the first one, the fourth one, the first one the same, and the fifth one, the first one, the third one the same, and the second one and this fifth one are the same, but the third one and the last one are the same. The sequence has 7 formulas, and the 7 components must obey the agreement of each other under this particular specification. That's why I say this is called a type specification. Well, we call this syntactical type definition. If you consider all those sequences, and that gives you this. This is the formula. That's a Frege's rule. In every course of logic, you find out the first axiom of logic is like this. Okay, our theoretical setting is like this. We can very clearly what kind of type definition we have, how many gaps we have, how they are organized. I want to emphasize this guy is a set. It's not a sample. A sample just for all to read this object. It's a set. It's existence. Okay. So based on this, you can find out that we have another law of logic. That's a three-dimensional mapping into this form. Okay, you just organize the three arbitrary independent formulas, you put them in this type. So this you can prove this is a law of logic. And each value is logical true. So you can see really this is really a logical in the set theoretical part, its existence. Okay, so I have another example which I may not have time to give the details, but I will explain to you how the universal quantification is. This I want to say in mathematical practice, and this is the Frege's rule. Everybody does. Everybody take it for granted. Everybody may not even realize you apply this one. Give you one example. Whenever you apply a definition to prove something, you are really apply this rule. Specialization. Okay? So of course you have to redefine the domain of the mapping, and it can be defined, and then you have a mapping of this form. That's really the mapping give you. This is a definition of this particular domain of this mapping. And domain, again, is very effectively checkable, and these claims are formally deducible, definable. Okay, finally, that's what we call sometimes you want to introduce some dummy variables. It's again another Frege's rule. Every practical mathematician use it, but not necessarily everybody realize they apply this Frege's rule. If I do set theory before do this calculation, I myself did not realize there's something supporting us. We can do things correctly because of this reason. Okay. The equality axioms, so I think I just jump it. Just tell you, we do have this type of logical laws, but again, the definition, the domain has to be defined effectively. But in set theory, in the formalized theory, we can do it without a difficulty. Okay, so these are the things. Of course, there's some examples, meaning that you have to be very careful. Not necessarily there's a one-to-one correspondence of the laws of logic with these kind of forms. And they may mean something different. Therefore, the type definition stands for another independent ingredients. Okay, they are not necessarily have the forms. You must have the same definition. Works out. It's not. So this is just give you an example of this type. Okay, so we can define a sentence is logically true if it is an instance of the values of some law of logic, which is determined completely by its logical form and the syntactical definition of anticipated sequence of some formula. So that's our definition, and a clear rewrite about the Quine's definition. So we give a reinterpretation of Quine's trying to do. Of course, you can do the computation, find out Quine's definition is only a sufficient condition, because you can provability to the complexity computation that comes to the Professor Chong was talking about the delta 1, or sigma 1, pi 1. So this type of things can tell you how complicated the definition should be. It's not necessarily by what the Quine tried to do. This is only sufficient condition. Okay, so then we have this logical truth, and we have this definition stuff, and we can have this in summary. The logical form, that's a specific way to use logical constants, the syntactical type definition of anticipating sequence of subformula, and we have the abstract modeling of objects with the object language is designed to describe. The metaphysical truth definition of sentences among those structures. So these are standard practices in mathematical logic. Thank you.
Okay, thank you, Professor Feng. Very nice talk. And any questions from our audience? Okay, I have one. Speaking of the meta theory or do you have a kind of meta logic that can be used to build up a computer system, for example, a proof assistant or something like that?
Frege-Russell.
Mm.
Exactly. You have to use Frege-Russell. Okay. I mean, people are talking about the machinery proving mechanical proof of theorems. They do everything, but they forgot about Frege. Just like every standard practice doing mathematics without mentioning Frege. By the way, Russell White has a huge book, completely ignore Frege, which is unbelievable.
How do you
Frege system so far is the only one system in first logical, I mean equivalence form is different, been proved to be complete by Gödel. Therefore, that's why mathematics can be no problem. You carry out the logical deductions, you're not going to face anything difficult unless you assume something different. Otherwise, the logic is sound complete. That's Gödel's theorem. So if you want to do theorem proving, you better remember Frege's rule where to apply it. Otherwise, I don't think, I mean, the interesting part is we do the formal deduction. You feel there's a very calmly over there. You want to cross it, there's a river, you don't have a bridge. Then you look at, you search what Frege said. You find, hey, here it goes, there's a bridge. Go through smoothly. Very powerful. If you apply the correct instances of Frege's rules, the whole argument just goes through mechanically. But to choose which one to use, that's intelligence. I'm not so sure the AI will do.
Okay. Thank you. Any other question?
Okay.
Okay, so let's thank our speaker again.